Okay, so we've learned a fair amount now about what it means to divide and what it means to be a divisor. Another good question, which is, well, another interesting question, is how many divisors does a number have? Let's just take an example here and start with that, and then see if we can't, you know, come up with a nice, clever way to do this. So how many divisors? I'm going to abbreviate that with HMD. How many divisors does 24 have? All right, well, one easy way to do it is to list, and we've gotten pretty good at listing the divisors here based on our previous one. So if we make a list, we say, okay, well, there's 1, and then there's also 24, and then there's 2, and then 12, and then 3, and then 8, and 4, and 6, and that's it. So if we list all those and then count them, we get 1, 2, 3, 4, 5, 6, 7, 8. 8 divisors. So the answer is, how many divisors of 24 is 8. As the next question, let's do another example. That was a pretty easy example. Listing them was not so hard. Let's say, how many divisors does 571,450 have? Okay, now this one we can start listing, but I'm going to tell you there's actually quite a few of them, so listing is maybe not the best way to do it. So let's pause for a second here, and then we will come back to this and we will think, how can we maybe do this a little bit more intelligently? Right. So what we're going to do is we're going to take this and hold off on it for the time being. So let's go back to this first example and think, is there another way we could have done this for 24? Is there another way we could have figured out that there are 8 divisors, maybe without listing them? Because in all reality, the question doesn't say what are the divisors of 24, it says how many. So we don't really need to know what they are, we just need to know how many there are. Okay, well, let's start by prime factoring. Prime factoring 24. All right, so prime factors of 24, well, for 24 is 8 times 3, and 8 is 2 times 2 times 2 times 3, which we normally would write as 2 cubed times 3. Okay, so those are the prime factors of 24. Now, while we're at it, let's go ahead and prime factor all the rest of the factors. So, and we started with 24, so let's work our way down. So 12 is 2 times 2 times 3, or 2 squared times 3. 8 is 2 times 2 times 2, which is 2 cubed. 6 is just 2 times 3, which is just, again, 2 times 3. 4 is 2 times 2, or 2 squared. 3 is just 3, is just 3. And 2 is just 2, is also just 2. And then 1 is 1. Is 1. Now I filled in those 3 columns kind of for a reason. Okay, now if you look at these guys here, we'll skip 1 for the time being. All right, these are all the prime factors on this side here. You see that the only numbers involved in the prime factors are 2 and 3. Now sometimes one of the numbers is missing, like in this one we had no 3, it's just 2 cubed to be precise. And then some of the times the other one's missing, so like here 3 is just 3, there's no 2. But In any case, there's no other numbers. It's pretty clear that if you prime factor a number, any of its divisors will have the same primes will go in. They might go in different powers. As a matter of fact, they will go in different powers, but they won't have any other prime factors. For example, if 5 is not a prime factor of a certain number, then 5 will not be a prime factor of one of its divisors. So let's say that our p prime does not divide n. That implies that p does not divide a divisor of n. Alright, now we can prove that by contradiction. Let's say if p did divide a divisor of n, that means that that means that the divisor is equal to the prime times some integer, call it k. Well, we also know that the divisor divides the number. We can write the divisor, we can write n is equal to d sub n times, let's say, l. Now, if I substitute for this, I get pkl, and kl is an integer, so we see here that this implies that p divides n. So, in other words, if a prime divides a divisor, then it must divide the larger number. Alright, that was just an aside. Alright, so we see that the divisors are in there. And if we actually list our prime factors like this, if we say 2, 2, 2, 3, right? Well, we've already talked about subsets. We know that there are, you know, a bunch of, well, we can take all sorts of subsets in here. And if you look, actually, these divisors correspond to all of the subsets of this. So we could have 1, 2, which is there. We could have, let's do this. So if I just took 1, 2, that corresponds there. If I had 2 2's, these guys, that would be 2 squared, which is 4. If I had 3 2's, that's 2 cubed, which is 8. If I had 1, 2, and a 3, that's 2 and 3, that gives me 6, which is right there. If I had 2 2's and a 3, that's 2 2's and a 3 is right there, which is 12, and 3 2's and a 3 is 24, the number itself, and the last one is just 3, that's the only one I missed, which is just 3 all by itself, right there. Now that actually, if you think about it that way, that makes this number 1 make a little bit more sense, and we can write the number 1 as 2 to the 0 times 3 to the 0. In other words, there's no zeros, or no 2's and no 3's. This one is 1, 2, and no 3's. This one is no 2's and 1, 3. Here we've got 2 2's and no 3's. Here we've got 1, 2, and 1, 3. Here we've got 3 2's and no 3's. Here we have 2 2's and 1, 3. And here we have 3 2's and 1, 3. Okay, so here we have all of the possible exponents of 2 and all of the possible exponents of 1, of 3, sorry, and all the combinations of those. So instead of counting all the divisors, maybe we could just think about the exponents. So there's 3 2's, so the exponent of 2 can be 0, 1, 2, or 3. We see here's a 0, here's a 1, here's a 2, here's a 3. And the exponent of 3 can be 0 or 1. So we have 4 possibilities for 2 and 2 possibilities for 3, and if we take 4 times 2, we get 8, which means there's going to be 8 divisors of our number. And that corresponds with the count we had from before. All right, cool.